Alright, welcome back. This is homework number 2 in our Thermodynamics 1 class out of Koretsky's textbook. Now again, I do things a little out of order, as it were. And so we're doing pieces of chapter 2. Not all of chapter 2, but pieces of chapter 2. Basically everything associated with energy. Okay? And so our first homework question says, a rock with a mass of 9 kilograms is dropped 20 meters from a cliff. Okay. So we have a cliff, we have a rock, and, okay, so this is 20 meters. Okay. This is 9 kilograms. Okay. How much kinetic energy did it change? Okay, so we always draw a picture. Okay, and our picture in this case is, is this, and then we draw a boundary. Our boundary is the rock. Okay. So how much kinetic energy is that rock gaining? Okay. Well, kinetic energy is equal to 1/2 mv squared. Okay. So let's write down some assumptions. Okay. For this one, we don't need to really, we're going to assume that, internal energy doesn't change. It's about 0. Any energy transfer is from potential energy to kinetic energy. So we're going from potential energy to kinetic energy. Alright, so we're going to assume that delta U is 0. I don't know really if there's anything else that we could assume. I guess, rock stays intact. Rock's mass constant. That doesn't like splinter off into pebbles, or the abrasion of the wind wears it down, or anything goofy like that. So that's probably good for assumptions right now. Again, we should always add assumptions as we go along as we need them. But right now, that's probably good enough. Now, it's saying how much kinetic energy. Well, I know the mass. I know half. Oh, that should be a squiggly. But I don't know the velocity. Okay. I could calculate the velocity using simple dynamics, but really, because of my assumption that, so I'm assuming that, all PE is going to KE. Okay. Well, I can assume that any kinetic energy I gain is potential energy I lost. And so I can look at the potential energy formula, which says mass times gravity times height, or Z sometimes. We like to use Z, because why do we use Z versus H? Well, H is enthalpy, and so it's just easier to do mgz. Okay. Well, so this 20 meters here. Well, that's our Z. Okay, or at least our delta Z. Okay. And so mass. Okay, we got that. Gravity. Well, gravity's 9.81 meters per second squared. So it looks like I have enough. But let's check our kind of units. I should get either joules, or some variation thereof, or joules per kilogram. Well, it's on a mass. Its mass is in there, so this is not on a mass basis. So I should just get joules. Okay, so I have kilograms. I've got meters per second squared, and then I got meters. Okay, yeah, kilograms, meters squared per second squared. That is, that is an energy. That is a joule, so I'm good to go. So I am going to get joules when I'm all said and done. So all I do is just say, okay, 9 times 9.81 times 20, and then I'm going to get my answer. Okay, that's pretty straightforward. This is a pretty straightforward problem, but the other part of the problem says, oh, and Oh, if I calculate that, let's see here, that's 9.81 is about 10, so 90 times 20 is about 1,800. Well, it's not exactly 10, so we'll say this is 1,700 joules. So it's about 1.7 kilojoules. Okay. Yeah, I mean that seems reasonable. Okay. Maybe not, but we're ballparking here. So, assume all the kinetic energy was transferred to the internal energy of 9 kilograms of liquid water at 298.15 K. It's 25 degrees Celsius. It's just easier to write K than degrees Celsius. All right. How much would the temperature change upon the energy transfer? So this now has become so we're going to call this, we'll call this energy. This has now become a steam table problem. And now we're, all E is transferred, shorthanded. On the homework, I'd want you to put all energy is transferred to the water, so apparently it's landing in a lake in here somewhere, or rather, not a lake because 9 kilograms is not much of a lake. It's landing in a bucket, I guess. And so, and that bucket's at 25 degrees Celsius. We got to assume, now we do have to assume that, this is adiabatic, that, no heat is lost upon the heat transfer. So, and that's kind of all E is transferred, but that's one we want to get in the habit of thinking about is adiabatic. Okay, so this is a steam table problem, so we need to look up stuff in the steam table. I'm going to erase my picture, though. So I have my energy, so I go to the next part of the problem. Okay, I've got water. Okay, so I've got at T equals 25 degrees Celsius, and, P is equal to 1 atm, which means I'm liquid water. But I'm going to assume that that's basically, so I'm assuming that subcooled is same as saturated liquid. So that's an assumption, but it's not a bad assumption. It's an okay assumption. So instead of P equals 1 atm, because I don't have that in my steam table, I do have this though. So I'm going to assume my axis, my quality is equal to 0, and then my temperature is 25 degrees Celsius. So I go to 25 degrees Celsius. Okay. And what I'm asking for is, I increase the energy. So I have an energy, U liquid equals 104.86 kilojoules per kilogram. Okay. Kilojoules per kilogram. All right. Well, this was joules, or 1.7 kilojoules, but that was not per kilogram, so I really need to divide that by 9, which is, again, that 20 times 9, 20 times 9. So let's just say this is about, I don't know, what's there, 9.8 times 2 would be times the half? What am I missing? I'm missing something here. That math can't be right. 9.9 times 10 times 20. So it was 90 times 20. Okay, now I'm dividing this by 9, so that's about 1.8 or 1.9. Okay, so about 1.9. Oh gosh. I am having just the worst brain fart right now. So 10 times that guy, so 10 times 80, 890, why 10? Why am I trying to divide by 2? I'm trying to divide this by 9, so 10 times this, so 98.1, duh. Or, well, 98.1 times 2, which would be 196. So 98.81 times 20 meters. Okay, so that's 98.1 times 2. 98.1 times 2 would be 196.2 joules. So this is more like, well, that can't be right. Oh, and then I times it by 9. I was like, how am I supposed to get 1.7? Okay, so really, yeah, I mean, that is right. I'm increasing this by 0.1962 kilojoules per kilogram. That is not a lot. I mean, look at that. That's not. I'm 105 versus 104.86. Now, in this case, what I need to do is I need to interpolate. So, I need to interpolate between this at 25 and the other one at 30. Okay. So my other one's 125, but I'm not even good. So my other one is 125. Okay. Well, I'm not even going to raise my temperature 5 degrees Celsius. I mean, I'm not going to do the math and do the interpolation, but you can see here how minuscule changes in kinetic energy are. Same thing with potential energy. Okay. We dropped a rock 20 meters. That's about 70 feet. I think approximately it's going to reach a speed, approximately, like 40 miles an hour. That's still nothing compared to its potential energy, compared to its internal energy. Okay. And this is why we typically don't account for potential energy changes or kinetic energy changes in our processes, because it's just so minuscule compared to the kinds of changes we see with internal energy or potential energy. So I mean, this only probably is going to increase the temperature by like 1/2 of a degree at most.